Let's talk about uranium-based reactors. I mean, natural uranium-based reactors. And, and let's have a rough sketch of this uranium reactor. And let's go with it and try to talk about it a little bit. What it has, it has a shield. It's a concrete shield. And it has, okay, let me clear it. Okay, so what it has fuel rods and and moderators like graphite. This graphite is a heterogeneous moderator, and cadmium rods. At some points, they have rods. So the first reactor that was constructed, it was constructed in 1942 in under the guidance of Enrico Fermi at Chicago University, and it was designed in its simplest form, and it consists of a rectangular block, the way I'm showing, made of graphite bricks surrounded by concrete shielding, and there are some holes in the graphite bricks. You have holes in graphite bricks, and the graphite is acting as moderator here. And in some of the holes, what we do is the uranium rods are inserted. Fuel rods, what we call as fuel rods. Uranium rods are inserted with aluminum cover, and this aluminum cover that these rods have, they avoid oxidation of uranium. And in some other holes that we have, the cadmium rods are inserted to control the fission reaction. And a majority of the existing reactors are of this type. The majority of these nuclear reactors in the present world are of this type. And in this type, the fuel is basically, it is natural uranium, which has two isotopes, U-235 and U-238. And their ratio is 1 in 137.8 only. So this uranium 235 that we have, this is the only thing that undergoes fission with thermal neutrons. So the uranium is distributed in the moderator in such a way that the fast fission neutrons from a piece of uranium, they are slowed down. They are slowed down by moderators. So when you have those fast-moving neutrons, they are slowed down before reaching the next piece, and this fission takes place in 235. And whereas what happens here is that some thermal neutrons are absorbed by the neutron showers that we have. Some of them are absorbed by uranium 238 that we have, and what is formed is Pu, plutonium 239. So ordinary water as moderator has the highest slowing down power and an appreciable neutron absorption cross section. At the same time, now if the reactor fuel contains enriched 235, then ordinary water can also be used instead of heavy water. Now, a simple reactor employing ordinary water is simply known as swimming pool swimming pool reactor, and is very convenient for experimental studies. for many of the external studies. Now, the major part of this ordinary uranium, that is uranium 238, in which we have only 0.7% of uranium 235. So we have fission in 235, and is very costly because its quantity is very less, so it is very costly, and would certainly lead to an early depletion of uranium reservoirs that are present on this planet. So, when this uranium 235 that we have, when it undergoes the initial fission, the number of fast neutrons that we have, the fast neutrons that are available for further fission, is nearly 2.18 per fission. Okay, so out of which one neutron is used for further fission. And what was the remaining number of neutrons is 1.18. Now, what happens with this 1.18 neutrons? Now, if the core of the reactor is suppose this is the core, and it is enclosed in some blanket made of a blanket of natural uranium, preferably uranium 238. So what happens here is that these 1.18 neutrons that we have per fission, which escape from the core, they are not contributing to the nuclear fission, may be slowed down and captured by the blanket of natural uranium 238. And what it does at the same time is that this shield, the blanket of uranium 238, the nuclides of U-238, they produce what? They produce plutonium 239, which is as good as, perhaps even better. It is better than uranium 235 as a fissionable material. Thus, a composite reactor of this type can produce more fissionable material in the blanket, than it consumes in its core. In its core, it's consuming uranium 235. But at the same time, in the blanket, what we have, there's a transformation of uranium 238 to plutonium 239, which is as good as, even better than that of uranium 235. Such a nuclear reactor that we will have, this nuclear reactor is called fast breeder reactor. Now, besides natural uranium, thorium can also be used as a blanket to this nuclear fission reaction, because it produces. If we will use thorium here as a blanket, what it does, it produces U-233. This is also fissionable. And the quantity of the substance that are produced in terms of plutonium and in terms of uranium-233 in these reactors is more than that of the quantity of the fissionable material that has been consumed, thereby justifying the name breeder reactor. So this is how a reactor is designed, where we are consuming uranium-235, but at the same time we are producing more fissionable material in the blanket, which is being transformed into more elements like plutonium if we have uranium-238 as a blanket. So what is being observed here is that, what's the beauty of the thing here is that the quantum of particles that you are exhausting for developing the energy is less than that of the quantum of particles that we are generating in this blanket. Now, in these fast breeder reactors, because of small size of the core and the high power output, the coolants should have certainly good heat transfer properties. The coolants that are surrounding this system where we have this blanket, and it should it should be a poor moderator of neutrons. The best coolants that satisfy these requirements are called liquid metals, or called liquid metals, and such as sodium and sodium potassium alloys. These are acting as the liquid metal coolants. And this is the story of a breeder reactor, and the story of a uranium 238 reactor that I talked about.